Hi, everyone. Thank you for joining us tonight for a really exciting lecture. It was 75 years ago this month that LASP launched, originally as the Upper Air Laboratory here at what was just CU at the time. It was the only campus. And so you'll be hearing a lot more about the history, but also getting a glimpse of our present and our exciting future. So we have three speakers. The first will be Dr. Daniel Baker, who is the director of LASP, as well as a distinguished professor of planetary and space physics at CU Boulder. He currently holds the Mug Broad Reach Endowed Chair of Space Sciences on campus. Prior to joining LASP, he was division chief at NASA's Goddard Space Flight Center. He's a lead investigator on numerous NASA space missions, and throughout his career has received many honors. These include being an elected member of the U.S. National Academies. In 2016, Dr. Baker also received the Colorado Governor's Award for high impact research related to his space weather scientific research. He was awarded the American Geophysical Union's highest honor, the William Bowie Medal, in 2018, and the Hannes Alfvén Medal of the European Geosciences Union the year after in 2019. Our second speaker tonight will be Dr. Fran Bagenal, a research scientist at LASP and a professor emerita of CU Boulder. She's a co-investigator and team leader of the plasma investigations on NASA's New Horizons mission to Pluto and NASA's Juno mission to Jupiter. Her main area of expertise is the study of charged particles trapped in planetary magnetic fields and the interaction of plasmas with the atmospheres of planetary objects, particularly in the outer solar system. She's participated in several of NASA's planetary exploration missions, including Voyager 1 and 2, Galileo, Deep Space One, New Horizons, and of course, Juno. After her election to the National Academy of Sciences in 2021, she led the Academy's studies of demographics of the space sciences workforce. Dr. Pam Millar will be our third speaker tonight. In her role as LASP Deputy Director of Strategic Development and Communications, she enables growth by strategically identifying, assessing, and implementing ongoing and new research opportunities with federal agencies and the commercial space sector. Before joining LASP, she worked for 3 decades at NASA, including 5 years as the director of the Earth Science Technology Office within the Earth Science Division at NASA headquarters. Throughout her career, Dr. Millar has fostered a community of female scientists through workshops and mentoring throughout her career. So with no further ado, I'm going to turn it over to Dr. Baker.
Do we have to start this? You know how to start this? Okay. Good evening, welcome everyone. A colleague asked me the other day, didn't you have a 70th anniversary? Are you going to have galas every 5 years? My answer was, no, I don't think so. But when you have the Diamond Jubilee year, it's hard to resist the opportunity to celebrate. The 70th anniversary, I think we looked around and sort of looked backward at what had been accomplished. I think our goal now is to try to look more forward. I'm going to look back a little bit, but I'm going to try to talk more about where we are. You might say, well, are we going to look forward a great distance? Well, Pam's going to talk about how we're going to try to look forward maybe a bit further. But I think we're just beginning to take the next step toward the next 75 years now. 3 years and 20 days ago, our world came crashing down as much of the world's population faced the COVID pandemic. And to say that this has been a challenging time for science, challenging time for LASP would be an understatement. But what we're really trying to do is to use this post-COVID time to take a new look at ourselves, think about where we might go from here. And our theme now for LASP, I would say, is delivering the future of space science. And so what we want to do tonight is explore some of the history, some of the status, and look at the things we have more or less in hand, and think about how these will be a springboard to the future. So the early years, the physics department at the University of Colorado got involved with the Naval Research Laboratory and the Air Force, which was founded in September of, became a separate service in September of 1947. And they began research developing rocket payloads to study ultraviolet radiation. And as Terry indicated, in 1948, the university formed the Upper Air Laboratory. So there's a memo that was issued on the 13th of April, 1948, that established that the Upper Air Laboratory would exist. The Upper Air Laboratory, and this is all long before NASA formed, so this is some of the first activity in space, really. The Upper Air Laboratory developed instruments, and in 1956, it says here, people left to form Ball Brothers Research. I would say it's more accurate to say that they were poached by Ed Ball, who was looking for something to be involved in government research, as Ball Corporation had been during World War II. And a number of things failed, but the aerospace research that is now Ball Aerospace, of course, became very successful. NASA was formed in '58. And then the research really began in earnest to explore the upper air, the upper parts of the Earth, to study the planets and to really try to understand the influence of the sun. And of course, now LASP has been involved in missions to essentially every planet in the solar system, as we'll talk about. These are some pictures of the, on the left here is the V2 rocket. If you look carefully at this, it says that this is an image from 1951, I believe, at White Sands. The label on here says LASP, but LASP didn't exist as an entity until some years later. The right side is the Aerobee rocket. For those of you who've been in the LASP Technology Building, there's an Aerobee rocket suspended there. It's an interesting thing that my old mentor, James Van Allen, was the co-chair of the committee that got together to develop rockets, civilian rockets, that would become the workhorse of the space program to take the place of the V2 rockets that were, of course, limited in number. And the Aerobee rockets have served very well over time. Here is on the left side is a picture of the two people, or at least one person, who was really instrumental in the formation of the Upper Air Laboratory, William Pietenpaul. He was the chair of the physics department at CU. And he's being presented an award for 30 years of service. And this is a picture taken in 1950, in April 1950, so 2 years after the formation of the Upper Air Laboratory. The award is being handed to him by Oliver Lester, who unfortunately died just about a year after this time. But Pietenpaul was really instrumental in assuring that space research, rocket research would really go on. On the right side, you see a sketch of the key kind of capability, engineering capability, that allowed instruments to point at objects like the sun or a particular place in the atmosphere. This biaxial pointing system was one of the things that really attracted or led to the idea of the individuals going over to form their own corporation at Ball. And this became a very successful thing. It was used by many, many researchers around the world. So these are some pictures. This is from the Denver Post, dated the day of the formation of the Upper Air Laboratory. It says $69,000 for research. In 2023 dollars, that's about $825,000, which is not a huge amount of money, but it's nothing to be sneezed at either. It was really quite a coup to land that kind of resource in those days. This is a picture in 1950 when Frank Waltz was brought in by Pietenpaul to lead the development of the solar pointing system. And these are some of the first results from the biaxial pointing instrument that for Lyman alpha from the sun. And this is the space science building. It was the little house on the prairie, I guess you could say, at that time on the campus. This is the core of what is now the Duane Center on the main campus. This was built with funding from NASA. $729,000 grant was given to the university. Actually, there were several universities that received funding for bricks and mortar back at that time, and CU was a proud recipient of some of that. So if we look at and we're going to look at the sweep of activities over these past 75 years, but starting with the rocket activity way back when, going to modern things. This is a picture of the Emirates Mars spacecraft, the HOPE mission. And so we can really say that, make a claim that no other academic institute can make, that we've sent instruments to every planet in the solar system and beyond being Pluto and minor planets. How do we fit into the ecosystem here at the University of Colorado? Well, there are a number of very prominent departments, academic departments where professors teach and where students get their degrees. But LASP is one of the institutes, and in fact is one of the largest institutes on the campus. There's also GILA. You can see my pointer, I don't know if you can see it, yeah. And the Cooperative Institute for Research in Environmental Science series. They're affiliated with some of the Department of Commerce institutes here in town. We're also very proud that we worked aggressively to bring the National Solar Observatory to Boulder. Of course, NCAR has been here since the 1960s or so, and much of our work is supported by NASA, obviously. The people are what make things really tick, and this shows from about 2006 onward, the growth in the number of people, also the categories, science, engineering, students, undergraduate and graduate students, and we have about 180 students working at LASP right now. The facilities are very spread out. We have the building you're sitting in now. This is very sensitive. Here's the Space Technology Building. Here's the annex that was built in 2006 or so, 2005. Caroline Himes is here tonight. She helped make that a reality. We're, of course, over here in the science building. We have the Dust Accelerator Lab, a fabulous place across the creek. We are also occupying now a major part of the Astrophysics Research Lab. And we have the Park Place facilities that we're taking over more space there all the time, and have a number of people in the administrative center also across the creek. We also, we need more space, and so we're in the process of trying to get a new building built. And we hope in that process that we'll be able to bring more of our people back in closer proximity, because people working together is really what makes everything successful. This is an eye test, but it tries to portray the range starting at the top, the sun, going out to the outer fringes of our solar system. And the horizontal axis is time. And this starts back in about the time of the formation or the renaming of the Upper Air Laboratory as LASP, but portrays the very extensive program of solar observations, planetary research, and in more recent times, just the density and variety of instruments that folks in LASP are part of. In such a short time, we of course can't talk about all these things, but we'll talk about some of them. There's a unique synergism within LASP. I think it's a key to the success of LASP, and that is that we're driven by science. The science questions are the place this all starts. And these are science questions about the planets, about our own Earth atmosphere and other planetary atmospheres, the sun, and now we've added stellar research to the solar research and space physics. To do this, we need to often to design, build, and test hardware. So engineering, Tom Sparn is here, I see, the director of engineering. We have mission operations and data systems. Chris Pankratz has just been appointed as the interim director for that domain, which is crucially important, and administration. I don't know if Stephen's here tonight, Stephen Edinger. Okay. And the science is headed by Frankie Parvier. Frank might wave at everyone there. And the combination of all of these capabilities of science, engineering, operations, and being able to carry out the administration and the contracting and all the procurements and so on is crucial for the success. So I'm going to show you some of in words, some of the science that we pursue. I'm going to also show you some examples. But I think you should realize that in this limited time, we can't do justice to all the things, but we hope over the course of the next year that many of you will be able to attend other activities, that you'll be able to see yourself in tours and so forth, a lot of things we're talking about here. But this kind of research, having well over 100 PhD scientists and students and staff to really carry out these investigations has been crucial. And the large number of planetary Earth orbiting missions, suborbital rockets, and now we're engaged in even smaller kind of space missions. It's really a very exciting time. The LASP engineering, again, this is meant to illustrate in a very compact way the fact that we carry out engineering on ground-based way and balloons, aircraft. We are involved in suborbital flight still. The rockets continue to be a key part of what we do. Low Earth orbit, where there's so much activity now commercially and extending out to geostationary orbit. We've also been involved in several lunar programs and deep space. And just recognizing that we do mission development, instrument development, component, key new technologies there, vehicle integration, mission operations. It's really a very complete sweep. And there are virtually no other university or academic institutes that have such a broad range of capabilities. In the mission operations sense, we're operating several NASA spacecraft. We're also operating literally hundreds of instruments, making measurements all around the system that I talked about, and developing a lot of the processes and the techniques for analyzing the data and distributing the data to not only our own community, but to the wider scientific community. And it's particularly exciting to realize the number of students, 30 or more students that are working alongside professionals to carry out this kind of acquisition and distribution of data. And the data systems themselves to develop new algorithms, to work on instrument calibration, to visualize the results, to have individual science centers and data processing systems for the many different missions we're part of, and to provide web services. All of these are key capabilities that, integrated together with the engineering, the science, really leads to the complete package. And we have to really, again, emphasize how crucial LASP being a part of the university and being so involved with students and having students so involved with LASP has been one of the great success stories. And the availability of students here, the close proximity to the main campus and to students that are in the various departments has really been a hallmark since the 1980s at least. I mentioned that we are really involved in a lot of things and are a large organization compared to many of the other entities on campus. This is, again, a bit of an eye chart, I guess, but just wanted to mention that LASP and series, as you see on the upper left there, bring in or certainly propose for huge amounts of money on an annual basis. The university overall has, I think this is from a couple of years ago, but CU has proposals that total about a couple of $2 billion. And LASP has roughly a quarter of those proposals and has about $500 million of grants and contract proposals that are out on the street now. So space research, and I include their series and parts of GILA and parts of other of the institutes. Space research is a huge part of what CU does. So let's talk about some of the successes and maybe what they portend. I don't believe Bruce Jokoski is around. I think he's traveling, but Bruce proposed and led one of the really successful missions to Mars. This is the MAVEN mission. This continues to operate very successfully in Mars orbit, has been following the water and understanding how Mars went from a warm, wet planet billions of years ago to the cold, dry planet we see today. And I think MAVEN's success led pretty directly to the involvement to bring a number of young engineers from the UAE, the United Arab Emirates, in 2014. Those folks came here stimulated by the success of MAVEN largely, and proposed to us that we might work with them to help celebrate the 50th anniversary of the founding of the UAE. And that initiated the development of a program which is called the HOPE mission. The HOPE mission is again in orbit around Mars, highly successful. It is returning beautiful data about the global Martian system. And maybe as important as the science of Amal, of the HOPE mission, is the tremendous success in a sociological sense of the growth and development of the relationship between the UAE and the University of Colorado, and the warm friendships and future success that was related to this relationship with the UAE. And toward the end, I'll talk about the next step that we're taking with the UAE, for example. Another area of investigation has been the Van Allen radiation belts have been with us. Of course, we've understood this in some ways, going back to the earliest satellite programs in 1958. Van Allen and coworkers discovered that the Earth is shrouded in high energy radiation belts. In 2012, we launched 2 new probes, which were called then the radiation belt storm probes, but they were quickly renamed as the Van Allen probes. They've returned beautiful data until the mission came to an end in 2019, but gave us key new insights into the structure and dynamics of the Earth's radiation belts. We are part of and co-leading the CU Space Weather Center, understanding the radiation environment in space, understanding the effects of the sun on the Earth and humans and technology is one of the key things related to the program at NASA called heliophysics. And CU Boulder, under the leadership of Tom Berger, has been pursuing a number of avenues, and LASP has been a very central part of this to try to develop new tools to understand and even forecast space weather and its effects on human technology. We're also excited to be part of new concepts, multi-spacecraft missions where multiple, usually identical spacecraft are flying in constellation in close proximity to one another and representing sort of an extended spacecraft, if you will. These MMS spacecraft have been flying just a few kilometers apart since the launch in 2015. And these spacecraft have on board key instruments from LASP. But we're also doing the science operations here. So there are 100 total instruments, and we've been doing the operations since the commissioning back in 2015. Another real innovation came with the GOLD mission. This was geared toward studying the Earth's upper atmosphere and really understanding the dynamics of the thermosphere. But this was not done in the usual way of launching it on a NASA spacecraft, but rather was hosted on an SES Americom commercial communications satellite. This was launched in 2018, was commissioned during that time, and has been operating beautifully since that time. And this represents, was one of the first NASA missions to be a hosted payload on a commercial satellite. I think this holds the potential in the future for rides to space on industry-provided commercial satellites. And so it's a key step toward the future. Another area that LASP has led in for a very long time now has been the understanding of the total and spectral irradiance of the sun. Understanding the energy coming from the sun and how it affects the upper atmosphere and the total atmosphere of the Earth is absolutely crucial. That is the backdrop upon which human change is superimposed. The climate change is superimposed on the natural variability of our atmosphere on Earth. And the TESIS spacecraft was launched and placed on the International Space Station back in December 2017. And this was the last view of TESIS seen on the International Space Station in the picture on the right there. So understanding the input to the system is very important, but also understanding the output. So understanding the entire energy budget for the Earth is crucial. And Peter Paluski and his team have been doing a marvelous job with they've now won a competition with NASA to do the Libra mission. This will provide the measurements of the albedo of the Earth. So we sort of master the input, and we now will master the output. So come 2027 or so, the Libra mission will be making these highly sensitive measurements of the energy that's leaving the Earth. And of course, that will help us to understand the overall energy balance within the system. I mentioned Frank is the senior scientist now within the lab. Frank is the lead on one of the key instruments on board the geostationary orbit environmental satellite system, GOES. These are large and very capable instruments that fly on these operational NOAA spacecraft, making exquisite measurements of the sun and its variability in the X-ray and extreme ultraviolet. And they're part of the system that provides the nightly weather pictures that you see on TV. These large instruments are, of course, very capable, but we've been looking at ways to try to reduce the size and the complexity of these instruments as much as possible. The compact total irradiance monitor is an example of that. On the left, you see an example of the kind of total irradiance monitor that was launched early in this century, say, and mass approaching 10 kilograms, relatively high power consumption. And with constant pressure, motion toward trying to reduce the mass and power consumption of these instruments, the compact total irradiance monitor, CTIM, which is launched in 2022, reduced the mass tremendously to about 0.5 kilogram, roughly a pound, and greatly reduced the power as well. So this is really one of the trends in the work that we're doing, and one of the areas that I think LASP is really cornering the market almost on, and that is to develop spacecraft that are really quite small but extremely capable and complex. The first of these was led by my close colleague Shinlin Lee, who proposed to do the Colorado Student Space Weather Experiment sponsored by the National Science Foundation. This was launched almost at the same time as the Van Allen probes and worked in conjunction with the Van Allen probes for 2 years. This was highly successful, led to a number of scientific publications. And now you can see the long list of CubeSats that have been developed, completed their missions, or are on orbit now, or are about to be. And these include solar instruments, space physics instruments, astrophysics missions, Earth science missions. There's almost no limit to what these small satellites can accomplish. One of the things that we were very excited to be part of through our partnership with Ball Aerospace was to do the mission operations for the Kepler program. This was a spacecraft that was geared toward looking for planets around other stars. The mission operations were done here at LASP, again with strong student involvement, I might add. Over 5,000 candidate exoplanets were found. 2,500 confirmed planets around other stars, just with the planets that were discovered by Kepler. And this really whetted our appetite, and we've been delighted that Kevin France, Brian Fleming, and their team have come back. This is sort of like Back to the Future, that CASA used to be part of LASP long ago, and now more astrophysics is coming back into the fold here at LASP. And one of the missions that we're very excited about is the ESCAPE mission, which was proposed and nearly succeeded a couple of years ago, but we're going to do this again and win it this time. But this is really to study Earth-like planets that are rather Earth-like, to study their atmospheres remotely. And these are planets that are orbiting around red dwarf stars, very active systems, and to be able to study the escape of the atmospheric constituents, somewhat a la MAVEN, but about planets that are far, far away from our own solar system. About 15 years ago or so, we decided also to make an investment in new kind of science for LASP, and this was cosmic dust. And so you might say, why do we want to study dust? Well, it really has the thumbprint of the origins of our solar system, and it is amazing the information that one can derive by using these sophisticated, as you can see, rather large instruments. The IDEX, the Interplanetary Dust Experiment, that's being prepared now for flight on the Interstellar Mapping and Acceleration Probe, IMAP, is one of the key instruments. IMAP will launch in 2025 or so. We're making great progress. The flight instrument is well along for IDEX now, and this dust instrument joins a truly beautiful instrument, the SUDA instrument that has just been delivered to JPL for flight on the Europa Clipper mission. These instruments are mind-boggling in their capability, but the ability of these instruments to fly through, let's say, near an icy moon or planet, to be able to look for the thumbprints of organic materials. And the guys in the lab here have put bacteria on ice grains, accelerated them in our dust accelerator, and then have been able to see as the bacteria break up, can see the amino acids, can reconstruct essentially the bacterium that was originally accelerated. fantastic way to look for life on other planets. And again, looking to the quite near future, we hope the Geospace Dynamics constellation is a 6-satellite mission that has been approved by NASA. We were selected, Lila Anderson is the principal investigator here, to have one of the key instruments, the ether instrument that's going to be on board GDC, making in situ measurements. And these are measurements that will be made in relatively low Earth orbit. This is a place where there are presently hundreds of operating communication satellites and other key Earth observing satellites. And if SpaceX and other companies have their way, there will be soon there'll be thousands. It's estimated that by 2030, there may be as many as 50,000 spacecraft doing various kinds of commercial work in low Earth orbit. We have to understand more about how the sun interacts with the upper atmosphere of the Earth. And I mentioned the continuing work with the UAE, the asteroid exploration program, MAX, is now well underway. We're going to build another spacecraft going to flying by 6 asteroids and then landing on a 7th one. And this is being done in cooperation again with the UAE and this time with the space agency in the United Arab Emirates. And this is going to be another exciting and amazing program from LASP. So I've probably taken more than my share of time here. Let me just say that in summary, some of the guiding principles I think we apply is that when opportunity knocks, we should answer the door. And I think we've tried to do that. I'm just trying to give you a hint of that here this evening. I think a key point is to give good people every chance to pursue their passions. And I can't say strongly enough that what makes LASP tick is really that we have so many people who are passionate about wanting to pursue and answer key scientific and technical questions. Don't limit the organization with artificial boundaries. As you've had a sense, we've grown, we've expanded, we've gone to different kinds of instrumentation, and I hope that will continue to be the case. And I think making good strategic alliances with departments, with other institutes here in the Front Range. We have an amazing aerospace ecosystem here in Colorado. And I think we're making good strategic alliances all the time. And we should, that should be the hallmark going forward. And when we get on a good path, we should follow where it leads. And I believe that Pam will talk about maybe how we follow those leads and how we jump off, how we use some of the things I've talked about as springboards. And with that, I think I'll turn it over to Fran.
Okay, thank you very much. Great pleasure to meet with you and to talk with you about the history of LASP and a little bit about current and future demographics. But most importantly, I want to really talk about the role LASP plays in the development of the US space science workforce. So if we look at the history, and Dan showed some of this expansion in the size of LASP over the past, here I have 41 years going back, and you can see that huge quantity of employees now, 70 people, the total, mixture of engineering and science, about 50-50 of each, plus mission operations and data systems, all growing, and the administration as well. Now, when we look at the past decade, more specifically, we can see the numbers have doubled or nearly doubled. Similar growth in both science and engineering, so these are sort of matching. But the real question is, and Pam will come back to this, we really have to think about how big do we want to grow. There are no other labs in the world, I believe, at a university that is doing space science at this scale. There is no other example. Yes, there are national labs. There are large federal research facilities, but at a university, we're the only one. And so we have to think about how we operate. We're not an aerospace company, we are a university. We have to think about this. So let's look at the current demographics. And I've got here undergraduate students, graduate students, research scientists, tenure track faculty. And you can sort of see that as a career track if you like. And then PRAs. The PRA is professional research assistant, which is the sort of label the university gives. But that includes things like mechanical engineers, system engineers, data scientists, and so on and so forth. They're sort of lumped together in that category. I'm going to focus on the science, and you'll see why in a minute. Now, when we look at this, we've got percentage here of the workforce who are US citizens. And what you'll notice is quite dramatically that the research scientists are only just about half and half US and non-US. This is a very important point that I will be emphasizing throughout. When we look at gender, what we see here is a little under half of the grad students are female, about a quarter of the research scientists, a small percentage of the tenure track faculty. And there's a small numbers here, so it's a little difficult to pay too much attention, but I think you'll find there's a big difference with age. That won't surprise you, perhaps. When we look at PRAs, it's about a quarter of the population. So now, I have spent a lot of the time the past 5 years or so looking at workforce surveys across NASA's divisions, particularly the heliophysics division and the planetary division, and then comparing them in National Academy studies of the workforce and what we need to do about the workforce. And what you'll see that, of course, science is largely white and male. That won't surprise you. The female population has been increasing, somewhere between 17% in heliophysics up to 38% in earth sciences. But of course, there's very small ethnic and racial minorities in the space sciences. Now let's think about things in a national perspective and then compare the international perspective. So when we look at the numbers of the bachelors in physics, and when we're talking space science, it's really the path. Most of the people who come through get degrees in undergraduate degrees in physics, and the numbers are not all that different in the other areas of the sciences. You'll see that in a minute. And what you'll see that since the beginning of the space age, it's been sort of fairly constant numbers, around 4,000 degrees produced in the US, until here we have about 98, but at the beginning of the 2000s, when the numbers began to take off. And people are realizing, I think, that, yeah, you can get a great job if you have a degree in physics. Numbers have been going up, and they've been going up since. But when you compare these numbers at a per capita production, so you look at different countries across the globe, and, you know, I use the American Institute of Physics. They deliver a lot of statistics that are useful to look at. What you see is that, in fact, the production of degrees in physics, both bachelors, the ones in blue, and in PhDs in red, the US is actually way down the league table. And you might be surprised to see which countries are ahead of the US per capita, okay? So, and I'll also point out that China and India are not included in these statistics because the American Institute of Physics couldn't get good numbers at the time they produced this report. So now let's think about physics education in the US and why is it we're in this state? So one thing to look at is to think about high school teaching in physics and the other sciences and compare them with the humanities and social sciences. And what you'll see is a really remarkable number that in the US, only 40 few percent, less than half of teachers teaching physics at high school have an undergraduate degree in physics. Now, here in Boulder, of course, being a town that has more PhDs in science than I think in just about anywhere else in the globe, we have, our high schools actually do have pretty well qualified teachers. But you go across the nation, particularly into poorer areas, rural areas, you may find that those high school teachers do not have much in the way. I mean, you know, the myth is that physics is taught by the football coach, right? I mean, that's the joke that people make, but it's a very serious issue. So then we have to think about what happens when people go from high school to college. And this has been shown for several studies over the decades, that the point where the percentage of women drops from roughly 50-50 at high school in various academic ranges, they drop down to 20% at the college level. So what happens is in that first year of college, where you have to take basic physics, first year of calculus and so on, that's the time when the percentage of women plummets and the percentage of underrepresented populations plummets. And this has been studied for many years. And the reasons are that the students come underprepared, and then they find when they get there, the quality of teaching is not particularly friendly and supportive. And there's this weed out culture that basically says you just have to be brilliant to survive, and the teaching puts people off. Now, this has been studied for the past 40, 50 years. And there are a couple of books, recent one coming out a couple of years ago called Talking About Leaving Revisited. And what they find by interviewing students across the country, that they find when they get to university, they're in these large classes, 350 students in a classroom, that they get really put off by STEM classes, particularly the physics and the calculus. And they decide to leave, excuse me. And the people, everybody complains across ethnic backgrounds, gender, everything. They all complain, but the white guys seem to persist and stay. Whereas the other population say, to heck with that, I'm going to go do something else. Okay? We know about this. We've known about it for decades and decades. The question is, what do we do about it? Okay, so then we move on to physics PhDs. And to be a professional scientist, you need to get a PhD. And what you'll find here is we look across as a function of time, numbers have gone up and down and so on. But and the number of women has been increasing. It's now up at about 20%. But there's an important point here is to look at the percentage of US and non-US. And I am right here. I was born in the UK. I studied, got my undergraduate degree in England. I came over to the US to do a PhD. I was so lucky. I arrived just as Voyager was about to be launched. And I started working on Jupiter, Saturn, Uranus, Neptune. Fantastic new data coming in from Voyager. And I went back to England to do a postdoc to London. But Britain was not really involved in the space business. And if I wanted to continue with Voyager and subsequent space missions, I had to come back to the US. Okay? And so I came here in 1989, joined the faculty, and I've been here since, became a US citizen in 2001, 6 days before 9/11, interesting enough. But the point I'm making is the US is relying on a large number of non-US educated and trained scientists who come into the US to form the population. And so far we've been fine, right? The lab has done well. Like I said, nearly half, just about half of the research scientists here. But there are a couple of National Academy reports that point out that this is a problem. So this one came out last year. The National Science Board pointed out that if you look at research funding, the US has been charging ahead and doing well, but China is catching up. Other countries too are fairly flat. And then we look at the number of science and engineering PhDs that the US is producing. China and India are beginning to produce a lot more than before. So the point here is that the US has relied on foreign trained workforce, and we cannot rely on that forever. And we need to think about the workforce training in our field. So they came out with a report that said very carefully that the STEM workforce relies heavily on foreign-born individuals who account for about 1/5 the STEM workforce, high proportions in certain fields. Space science is about 50%. But then there's another report, and the chairs of this committee were Neil Lane, who ran the NSF for many years, and Norm Augustine, you may remember, did one of the NASA studies of the Challenger disaster and so on. He was aerospace engineer. They have this book called Perils of Complacency that points out that we have to be careful. We cannot rely on this foreign science and engineering talent, partly because they're not being as welcome into the US, but really the problem is that we need to cultivate a better science and engineering workforce from within the US to supply the needs, but also to give everybody the opportunity to do all the fun things that we do in science. So what can we do at LASP? We can't fix undergraduate education. That's not our job. What we can do, though, is this. Several National Academy studies have shown that educational research has shown that early experiences in research can make a huge difference. It encourages students to persist, it inspires them to study, and they are more likely to stay on and finish up their math and their physics homework and to complete the program. And this is particularly true for underrepresented populations. So this is where LASP comes in. Since the early days, and I will give credit to Charles Barth for doing this from the beginning, we have brought in students into research, all sorts of areas of research, from the beginning of emission designing and thinking about it through to the designing, the building, the operating, and then analyzing the data. And all the way through, we have been involved in doing this at various different levels. So in conclusions, if we're going to really help the nation with this issue of training the next workforce, we need to think about things and how to move forward. So we need to continue and even expand the training we have of the next workforce in the space sciences. We need to collaborate with the different academic departments, the ones that Dan mentioned. We need to expand and enhance our research experience for undergraduate programs. We have a great program that Willow Reed runs in the summer program, but it's only a limited number of students. We could quadruple the number quite easily and bring them in over the summer and during the semester to get involved in educational projects. We could develop bridge programs with local community colleges, maybe go and work with underrepresented institutions across the state. And we could partner with minority serving institutions that are really interested in developing space programs. So now is the time to act. This has become a major focus at NASA, NSF, and various places. And we have a critical role in the nation of leading in how to engage students in research, which leads to a workforce that we will be employed across the country, and much needed in both industry and government activities in space science. And with that, I'll thank you very much.
It's on. Okay, thank you everybody for staying up so late. it's not quite past my bedtime, but close. So Dan and Fran really set the stage, and what I'm really gonna talk about and touch on is what do we need to think about doing in order to continue our successful future, set ourselves up for success. Okay, so I have it in 3 major themes. So we need to make sure we have a seat at the table in setting the national science priorities. And so I'll just show a chart on decadal surveys. Last month's public lecture by David Millaspina gave a very detailed view into that. So, and it's taped, so you can go see that if you want. The second most important theme is the role of commercial space. It has grown exponentially and provided a lot of opportunities for partnerships and also with government. And LASP is, as you heard from Dan, uniquely positioned to be successful, or I should say, continue to be successful with small sats and CubeSats. We know how to do things small and get big science out of that. And then to echo a lot of what Fran said, developing the next generation workforce is how we deliver the future, because it's not just delivering on the instrumentation, but it's also the workforce that's capable to do that. So here's a chart that shows all the decadal surveys that are sort of in play right now. So as a reminder, every 10 years, each NASA Science Division surveys progress in their field and sets the guidance for future plans. And it also sets the framework for the funding priorities. And so you can see, let me use let's see if you can see here. Okay, so I want to point you to this one. This is the solar and space physics. Dan actually co-chaired this. And Fran was involved in that as well. And Fran, oh, maybe not that one. Fran was involved in this one in planetary science. And the current one that's ongoing in heliophysics, CU Boulder with LASP, we have 10% of the committee members. And that's how we influence the future, is by being on these committees, which then set the stage for the next 10 years or so. So the scientists write white papers, and then there are committees that discuss everything. It's you probably can't see it, it's in very fine print, but it says consensus study report. So the idea is the reports are supposed to be consensus, and NASA, NOAA, and NSF use these as guidelines for funding. So the next step here, I want to talk about the role of small sats and CubeSats. On the right-hand side, you'll see 2 also National Academy studies. The first one in 2016 really talks about can you do science with CubeSats? And then just this past fall, there was one that jumped to leveraging commercial space for Earth and ocean remote sensing. And the report's not limited to that, and these are publicly available. So we jumped from can we do science to how do we leverage what's going on in commercial space. So I just want to briefly go through the history. In 1998, 2 universities, Cal Poly in San Luis Obispo and Stanford, started putting together kits so that students can be trained doing hands-on activities. And then you go down to that last bullet, we're still doing that, but now we're able to do science out of it. So we've come a long way. And in between, how did we get to that? So CubeSats they're small and modular and inexpensive to build and launch. Recently, due to commercial space, there's easier access to space. I have a chart on that next. And as I mentioned, the market is booming in all different areas that we can leverage. So you can get bus components, you can get buses. So Blue Canyon Technologies actually was a startup a while ago, and they spun off out of Ball Aerospace's Star Tracker group and took a bunch of LASP people as well. And so they've grown exponentially, and a lot of companies on the Front Range contribute to this big ecosystem, and space as a service has really boomed. You can there are brokers for launches There are buses that you can catch a ride on and they'll do the mission ops for you. It's just boundless. And Dan mentioned a little bit about the miniaturization of sensors. I mean, just look at your cell phones, the microprocessors and cameras in there some of those are up in space. And the government was a little bit late to the game. So NSF had their first solicitation in space weather, I believe, in 2006. And then NASA had a pilot program in 2010. And that's after doing some solicitations, that's when they're like, hey, we think we can do science with these small CubeSats. And they're catching up now. And they're not only funding tech demos, but they're funding missions that you can do science with. So it's pretty exciting. And DoD is also doing this as well. And what's also added to the boom, of course, is the affordability. And you've probably noticed that commercial communications are putting a lot of satellites up in low Earth orbit. And so they're creating these capabilities that we might be able to leverage. If you look at it from the science perspective, doing constellations, you have more of a capability to make simultaneous measurements globally, to measure physical phenomena as they happen, to get better resolution spatially and temporally. So it presents a lot of opportunity for us to leverage. And I believe, with that second decadal report, the Academy's report on leveraging commercial, we can definitely do science with CubeSats, and LASP is doing that now. And again, training the workforce with hands-on. So a big part of this, even when the government started funding these CubeSat demonstrations, et cetera, it was really hard to get a launch. But NASA also started a program, Venture Class Launch Initiative, and startups started building these smaller launch vehicles. So that's what you see all the way on the right. So you have dedicated launch vehicles for small sats, and you have commercial brokers that are putting a lot of them on there at the same time. And that makes it cheaper, more affordable. Another way to get into low Earth orbit is to hitch a ride on one of the ISS cargo resupply missions. And in the middle, you can be a secondary payload, although you don't have much control over where you go. You have to go where the primary goes. And I'll point out that NASA has a CubeSat launch initiative that significantly has subsidized these launches, especially for academia. And moving right along. So Dan showed the list of all the CubeSats. What this is a picture of that and color coded by the type of mission: astrophysics, earth science, heliophysics, and solar science. And what I wanted to point out was that 5 have been completed, 3 are on orbit, and of those, 100% success rate. So that's unheard of. We know how to do it. A lot of the big aerospace companies don't know how to do things small cheaply. And so that's where our big sweet spot is. And the other thing I want to point out is 12 of the 15 CubeSat projects have student involvement. And this didn't turn out so well. So this is another study, but it was done by the Office of Science and Technology Policy. So it talks about developing the next generation workforce. In 2021, the Biden-Harris administration had a National Space Council meeting, and they wanted to focus on building the STEM workforce. And so I'll just read this middle part. Use space activities and missions to inspire more people to explore STEM fields. And that is another thing that LASP is uniquely qualified to do, since we have the students here and 25% of our workforce here are students. I also wanted to get to some of the points that Fran was making, and I'll read this other part. It is imperative to ensure people of all backgrounds, particularly from underrepresented communities, have equitable access to STEM and space workforce opportunities. And I think this is where we can play a big role, because we've shown that we can do it internationally. If we can do it internationally, we should be able to do it with minority serving institutions. And what this chart is the Inspire Small SAP program led by Amal Chandran. I don't know if he's here or listening, but thank you, Amal. So it's the International Satellite Program in Research and Education. And the idea is to spread the cost. So it's not any one team that covers the cost of everything. So each team brings something to the table, and you can see by the bottom banner, all the different international institutions that are involved. And right now, we have 7. I believe 3 are in orbit right now. 1 is getting ready to launch next week, and then another one in July. So this is a very successful program, and it trains, not just trains the students, but helps build capacity for the next generation workforce and teaming. And this in particular is important because it helps foster international teams and collaborations that can then feed into us being able to do the larger missions. And now I want to go into the uniqueness of what LASP does with generating the next generation workforce. So on the top right there, you see that radome exists with the ground station in the building right across the parking lot there. And so what you do is you have students who are training to be flight controllers, and they are operating multi-million-dollar spacecraft. It's really impressive, because if you go and do a tour and you'll see them doing it, they're just have this huge smile across their face. And so the program selects 20 undergrads each spring. So we also use the Soaring Suborbital Space Program, which uses sounding rockets and high altitude balloons for students to work with faculty and researchers, and they get to do research. And it's a little cheaper to do these demonstrations than it is to put something into LEO. And you can also do useful things with them. So for example, we have a sounding rocket extreme UV variability experiment, EVE, and that's used to calibrate SDO. And so that's kind of exciting because it's involved with making the space missions better. Okay, and so this is Willow's baby, the research experience for for undergrads. So this is another thing that we can replicate more broadly. This is a very successful program. I think, what, 12 or 13 years straight. It's got a great reputation. There are others like this. These are NSF supported. There is no reason why NASA or NOAA or other government organizations can't contribute to programs like this that we can sponsor during the summer for students. So in this program in particular, they have the opportunity for research in solar and space physics, and they're paid, which is nice, and it's a 10-week program. And the areas span the field of solar and space physics, and it works in partnership with several other institutes around Boulder that are listed there. So if we could replicate the successful research program, that would uniquely position us. So I'm going to end with a summary of how we set ourselves up for success. So it's about driving the future, getting a seat at the table, taking an active role in setting the national priorities for science, and be the partner of choice. So there are a lot of opportunities with commercial space, with the government and other academic institutions and global partnerships. If we deliver, as we continue to do, we're going to be the partner of choice. And if we continue to do that, I think we'll be in good shape. And the last part is taking an ambitious stance on developing the future workforce. And that's including minority serving institutions. We have to do better in that area, and we are developing programs that we can use for capacity building. And I think that's how we deliver the future with a capable, diverse workforce and meeting our commitments. So that's all I have. Thank you.
All right, thank you, Pam. I don't want to get too close to you because it'll yell at me. Let's thank all of our speakers. Let me see your thing. Oh, in the interest of time, we're gonna keep Q&A short tonight. We'll do 2 questions in the room and 2 questions from online. So, we'll start with an online question. If our speakers don't mind coming to the front. I'm trying really hard not to have feedback. Okay, so this question asks that there haven't been very many missions to Uranus and Neptune. Is anyone working on an ice giant mission proposal, or are there any plans to involve LASP in any such missions?
We actually had a LASP mini workshop in this room last week of scientists interested in going to Uranus and Neptune. The Uranus mission was a top priority of the decadal survey in planetary science. And we're starting to get together and think about what we want to do. And we had half a dozen really good ideas of things that we want to do. So I think we're in good shape, and I will bet you we're going to have a LASP instrument on that mission to Uranus, which is a high priority for planetary science.
Some of us don't want to wait until 2050 to do these things. And so we've been talking to the United Launch Alliance that's working on nuclear propulsion. It would do so much for science if we could get places of interest faster. And I think nuclear propulsion is one of the ways to really achieve that. If we didn't have to wait for 2 years, to go to Mars, every 2 years to go to Mars, could get humans there in a few weeks or a couple of months instead of taking 6 months to get there. It would really solve a lot. But going to the outer planets is particularly crucial, and I think that's one of the things we want to really make sure that we're partners in that kind of a future.
Okay, I want to put that in context for you. I heard a talk, and there was someone in the audience that said, and this is about the Uranus mission, and they said someone in the 2nd grade right now will be publishing the first paper. That's how long it's going to take if we're not able to get there faster. So I just wanted to put that in context.
Are there any in the house questions? Yeah. Okay.
All right, we'll keep going online. Is anyone willing to estimate how many thesis committees Charles Barth sat on? So many of us owe him a great debt to him. You get me, 15 is the estimated
Well, he
guess.
must have been on hundreds of committees. But he was on many other committees, so there were probably hundreds of students. Yeah, there you go.
All right, so one last question then. Dan, could you discuss the Kessler syndrome of 30K to 50K commercial satellites?
Could I discuss what?
The Kessler syndrome?
Huge satellite constellations, 30,000 to 50,000.
Oh, yeah. I mean, I've gone on record as being very concerned about the human pollution of near-Earth space. And we've just seen, like 4 weeks ago or so, SpaceX put 7,350 new satellites in orbit. And it's getting very dense there, and it's going to get a lot more dense. And if we have tens of thousands of spacecraft, the chances are extremely good, since most of them don't have propulsion, that they're going to run into each other. They're going to create more debris. And anyone who saw the movie Gravity or something, what I could imagine, that can become a hellish place in a hurry. So I think we have to have policy control about how many spacecraft we put there. We also have to make sure that we have a much deeper understanding of how these spacecraft are affected by the heating of the atmosphere and changing their orbits and the possibility of colliding. So yeah, it could be a catastrophe waiting to happen if we don't get on top of the policy.
Thank you.
I just want to say thanks to all of you for being here. Thanks to my co-speakers, and we're going to be taking the next steps now to try to define our near-term and midterm future. If any of you are here in 75 years, please remember this night and think about where we were in the dawn of the space age, more or less, compared to what will probably be a very exciting space future. So thanks very much.